Okay, so one more example, and then we'll move on to what's called one-sided limits. So this one, limit as x approaches zero of 1 over x squared. So obviously zero is not in the domain. Now, using the methods that we saw in the last video, there is no way to simplify this. Cannot rationalize the numerator or the denominator. Can't factor it and cancel anything out. There's no way to do any of that. So really, we just need to think about the graph. So um, the graph of 1 over x squared looks like this. So now what is happening as x approaches zero? Well, we can see that it's moving to infinity. And actually, so it's moving to infinity, but you really don't say that. You say the limit does not exist. So infinity is not really an answer. But you can see if you plug in smaller and smaller numbers that are getting closer and closer to zero. So let's say 0.1, 0.01, 0.001, 0.0001, so on. The smaller these numbers get, the reciprocal, 1 over that number, will get bigger and bigger and bigger. So it'll go to infinity. And because it's squared, it doesn't really matter if these are positive or negative. So whenever you have one that goes to infinity, you don't put infinity, that does not exist. All right, so the last topic for this section is called one-sided limits. And I kind of mentioned this, or at least I've mentioned sides coming from the right side or coming from the left side. So we use this notation, the right-hand limit or the right side limit, x approaches a, and then we have the little plus sign because we're coming from the positive side. So we're talking about x, so x is positive, and we're coming from that direction with the right-hand limit. So that's what that means. We're coming this way to whatever the function is doing. And then left hand would be coming from the negative side or the left side of the x. So it doesn't have to be negative because we don't have to be at zero. All right, so as an example, so this is a very simple example. H of t is defined piecewise, so it's 0 if t is negative, and then 1 if t is non-negative. So this graph would look like this, and we'll kind of shade. So 0 on the negative side, we have a hole there because it's not equal to 0. It's equal to 0 here. And then at 1, we'll have a closed circle, and then it will come like that. So there's our graph. Obviously, it's not continuous. And so let's look at the left-hand limit. So as t approaches 0 from the negative side or the left side, it's actually usually not appropriate to say the negative side, because if t is approaching 2, you're not approaching from the negative numbers, you're approaching from the smaller side of 2, so the left side. So I may say that, but that's not really what I don't necessarily mean negative. So the limit of h of t, so that would just be 0, because as we come along this from the left side, we are at 0 until we get to 0. So the limit from the left side is 0. The limit from the right side, and we'll say 0 plus of h of t. Now we're coming this way, and so that would be 1. The value of the function is 1. The value of the function, so h of 0 is 1. And so we can see from these two things, especially, that it's not continuous, because for it to be continuous, all three of these things have to be equal. So it has to be the left limit, the right limit, and the value of the function have to be equal to the same number in order for it to be continuous. So we'd actually call this right continuous, because continuous, the right limit and the value of the function are the same. So that would be right continuous, but it's not continuous in the normal sense of the word like we're used to using it. All right, so like I just said, well, not exactly what I said, but the limit as x approaches a equals L if and only if the left and the right hand limits are both L. So in that last example, the limit, let's go back up there. So the limit in this one as t approaches 0 does not exist because these two are not equal. So for this to exist, these two have to be equal. And going back to the 1 over x squared, the left limit is approaching infinity, the right limit is approaching infinity. They're kind of doing the same thing, but again, infinity is not a number. It's a definitionally it's just saying that the function gets bigger and bigger as it approaches that whatever x is approaching, in this case 0. So don't think of this as equaling infinity, in other words. But in this case, these are not equal, so it's not, the limit does not exist, and of course it's not continuous. All right, so one last example, we just kind of have a couple of kind of generic functions here. So we have defined here, we have a hole, we have a jump, and then we have here we have a hole, and then it's defined right there for 5. So the limit as x approaches 2 from the left, so we're coming up from the left and we're approaching 2, and so that value would be 3. The limit as x approaches 2 from the right, now we're coming right there, that would be 1. The limit as x approaches 2 does not exist because these two are not equal. And since they're not equal, the limit cannot exist. The limit as x approaches 5 from the left, so now we're coming up this way, that would be 2. The limit as x approaches 5 from the right, that's coming to the same spot, that would also be 2. So the limit as x approaches 5 is 2. But what is f of 5? F of 5 is actually defined right there as 1. So the limit exists, but f is not continuous at x equals 5 because this does not equal that. And so that makes it not continuous. So go through these examples a couple of times. You want to be able to evaluate limits pretty easily. They don't get too complicated, but you need to know the methods for evaluating them. Sometimes you need to simplify, sometimes you need to rationalize the numerator. Sometimes you just need to look at the graph. And then also be very comfortable with the idea how the limit and continuity relate to each other. That's also very important for what we're going to be doing later. So if you have any questions, feel free to email me and I'll get those as soon as I can.